from Blockstream Research. We work on the future of Bitcoin. We're dreamers, so we dream about the future of Bitcoin in terms of decades. So not the next few months, but the next few decades. And simplicity is one of these things that we think are necessary for Bitcoin, which is a new scripting language that will solve many problems. And today I'll talk about that. So why are we here? What are we? Where do we want to be? Like, what is the problem we're trying to solve, right? So we all have an idea of Bitcoin, of digital money, and what the features it should have, right? The problems it should solve. So what we want to do is we want to send money to a person or to a recipient. And this can be a single person. This can be also multiple people, which we call multi-sig. So this could be a Lightning channel, which we call 𝐓𝐿C. This could be more complicated things like a DAO, which we don't have right now on Bitcoin. Any kinds of things. But it should, when I want to send my money, it should arrive at the right location. We want to store value. So there are some proposals right now. We want to scale Bitcoin. So Bitcoin layer 1 is obviously limited. So we want to, the idea is to go to layer 2s, to move these actions to layer 2s, to increase transaction throughput. And it should be cheap and efficient. So this, I think, this is what we can all agree on. But and I think we already solved a lot of these problems, or these goals. But we're not quite there yet. So okay. So where are we right now? So we can send coins. We can send coins to public keys. We can do 𝐻𝐿C, so we can do Lightning. We can do slightly more complicated things, but like I said, there are many applications, many ways I could make my money available to a use case, to a DAO, or to a zero knowledge rollup that we cannot do right now. So we're limited on where we can move our coins and do interesting things with this money. And Miniscript helps. So maybe you can raise hands. Who knows Miniscript? Is anybody? Yeah. Surprisingly, many people, mostly in the back. Technical part is in the back. So there's Bitcoin script, which makes Bitcoin. So all of these, if I send coins to somewhere, it uses a Bitcoin script. And there are many features of Bitcoin script, but almost nobody uses these features. Most features are not used because they're dangerous, they're scary. You could lose your money. And Miniscript helps with that because it enables you to write Bitcoin scripts in a structured way, and it gives you some guarantees. So basically, it tells you if you write it this way, the money will arrive at the right location, and you will not lose any funds in the future. Like if you use a time lock, it tells you in 10 years after the time lock has expired, after that's matured, you actually are able to, the money will arrive, you will have the money, you will not lose the money in 10 years. And there are applications like Liana Wallet that use this feature. Vaults are an interesting proposal. So this is the store of money idea. So it would be great to have a cold storage vault, and you can only move a certain percentage of the money out, and you can detect if a hacker tries to get the money out, and you can stop the hack. Also, one of the things right now is we have layer 2s. Obviously, we have at the layer 2 day, and many layer 2s propose new offloads. So Bitcoin script or Bitcoin is not enough to support all layer 2s. Even things like Lightning propose things such as any prep out. So it needs extensions to Bitcoin script to either to work completely or to become better. So Bitcoin script is not enough right now. There's a huge demand for extending Bitcoin script. And we also extend Bitcoin script step by step to solve some small problems. Whereas The alternative that we propose here is we want one big upgrade that solves all of these problems in one go. But this is kind of where we are right now. Simplicity to the rescue. So what we have seen where we are, we have seen where we want to be. So how can this simplicity help? What we want to do is we want to enable, if I want to send coins to some use case, to some recipient, if I want to make my coins available in some kind of way, simplicity should support that. So we want a scripting language that is able to cover all use cases, all imaginable use cases. We want that, like Miniscript, which makes Bitcoin script less scary because it gives you formal guarantees. We want that this scripting language, which we call simplicity, is formally correct. It's formally verifiable. So you know that when you send your coins to this simplicity 𝐕𝐶, it works in the way it's intended. We want to build all possible layer 2s, so we can actually show that all imaginable layer 2s are supported by the simplicity language. We can, if there are certain ways that we do not want to use simplicity, we can limit that, but in principle, everything is supported, or it's possible to support whatever we want to support. And this is the idea of the last soapbook. So maybe you've heard about this idea. Simplicity will not be the last soapbook, but the idea is that instead of having a lot of small upgrades to Bitcoin script or to Bitcoin, we do one big upgrade that covers a lot of use cases and that doesn't need many soapbox. Or for many things, you don't need a soapbox because it's already supported. And I will talk about what that means in more detail. And this should be fast, and this you should, to prevent DDoS, obviously, if you do something very complicated in layer 1, you should pay for that complicated computation. You shouldn't be able to DDoS the main chain. So there should be a smart fee function as well. Also, one of the things I forgot to say at the beginning is, this is obviously a technical talk, but if you have a question, just raise your hand, ask a question. And if you're bored, just raise your hand and say, I'm bored. And then I'll try to address that, okay? So let's go. So maybe we are all on the same page now. Maybe raise hands, have you understood roughly where I'm at right now? Some people, yeah. Maybe what we want to do, right? So we want to make Bitcoin smarter. We want to do more things with Bitcoin, with Bitcoin. We want to build new layer 2s. We want to build new applications, financial and otherwise. And simplicity is there to enable that in a secure way, in a future-proof way that doesn't destroy Bitcoin, but it extends Bitcoin in a safe way. So very quickly, how do you do simplicity? So first of all, you always encode some data. So there's some simplicity data format. You have some functions, so you have some mathematical functions like add 1, and we have an increment function, for instance. And then you can evaluate that function, which gives you a result. We have access to witness data and to introspection. And that's all you need. And then you just have a program. So this is what logs the 𝐕𝐶. And based on the witness data that you provide and based on the introspection, it tells you can spend 𝐕𝐶 or you cannot spend 𝐕𝐶. So that's basically already how it works with Bitcoin script. It also tells you spend or not spend. But this is much more general. And that's already the execution model for simplicity. So this is very general. So what you can do is you can do a computation off-chain, any kind of computation you want to do. For instance, as your knowledge proof verifier. So you can run a rollup, a layer 2 rollup, and you can do a state transition. You can do a proof that says this state transition or this rollup block is valid, which is very hard computation. And then you can verify this computation on-chain, which is easy. It's relatively easy, which is important because everybody has to do this verification. And you can do this on-chain very easily if you just verify the computation. This is kind of this dichotomy between computation and verification. Computation is always hard, and verification is always easy, much easier. Like computing is like solving a Sudoku puzzle, and verifying is like checking that a Sudoku puzzle is easy. That's much easier. Computation is like mining a block, and verifying is verifying a block. That's much easier. And simplicity can do any of this verification. So anything you can do off-chain, you can do off-chain. You can verify this thing on the main chain with simplicity support. There's obviously one downside, which is downside. There's a one limit, which is consensus limits. So we do not want to do DDoS. Or you might ask, this sounds very powerful. If you think about this, it's extremely powerful, but we do not want to DDoS the main chain. And so we have certain hard limits of what you can put on the main chain, which is reasonable. And there's one way around this. So there are certain things we might want to do, or we definitely want to do, like signature check, signature verification, and other things. And we need we do these things quite a lot. So almost every UTXO, I would say every UTXO has a signature check. So this should be easy and small. So we have these jets, which are shortcuts for common functions. So you have the simplicity program, which does a signature check, and we can compress it to like small bit, and this is what we call a jet. And you compress anything that is common. So you do addition, subtraction, hashing signatures, maybe as your knowledge verifier. You compress it into one little atom, which we call a jet. And when you see that jet, you have some optimized C code. So it's small and fast. And simplicity comes with a fixed, which we call catalog of jets. So we say, these are the use cases we're interested in. This is introspection we're interested in. This is what we want to have very fast, and the rest we can combine into. So you can combine jets as well to build more complicated, to do more complicated computations. Which is the last software idea. So why is simplicity the last software? Why might it be the last software? The idea is simplicity is general enough to cover a lot of use cases. So we have this rich catalog of jets. It's already pretty long. It's getting longer. And in the end, the community decides what they want, obviously. So we do not force anything upon you. But we give you the opportunity to choose, and we give you basically the horn of plenty, and you choose what you want. So one of the things we do is we expose elliptic internals, so you are able to work with elliptic curves in a very general way. You can do point additions and all kinds of things to build cryptographic primitives. You combine jets to solve, like each jet solves a specific problem, and you can combine multiple jets to solve new problems, and you can combine this again to solve even more problems. And you can do a lot with that in consensus limits. So jet is very small, combining to jet is very small, and small problems are within the consensus limits. So this is a very general paradigm to enable a lot of use cases. Obviously not all of the use cases, but a lot of use cases. Like this is a huge upgrade, and this will, like small soft forks, such as small soft forks like 𝗲𝗵𝐷 or any prep-out, you can just do immediately. You don't need a soft fork. It's just already included. So you don't need new opcodes for a lot of use cases, because you can just do those things already in simplicity. That's why it is the last software. And if you ever need a new software, it also makes it better, because simplicity is a what we call a prototyping language. And so the idea is, I want to make a new opcode, like the 𝗲𝗵𝐷 opcode. And in simplicity speak, this is a new jet. So we can already do these things in simplicity, but we want to make them more compact. And so we define a jet, which does the same thing like this implementation in simplicity. And we can, because you can already do these things in an unoptimized way, you can deploy this on a testnet if you disable consensus limits on the testnet. And on there you can try all possible opcodes already. There are no code changes required, so you just run this thing. So I say I want to do 𝗕𝐶𝐷𝐷. Okay, I write this very large simplicity program which does 𝗕𝐶𝐷𝐷. I can do that because simplicity is strong, but it's a very large program. I go on my testnet and deploy this script, and I can test this with my friends and with my community and see how it works and see if it works. And then what I can do is I can say, okay, I compress this into a jet. I write C code which is optimized, and if I want, I formally verify that the C code I wrote is equivalent to the large program that did 𝗕𝗏𝐶𝐷𝐷 on the testnet. And then once that's done, I add the jet to the catalog of the next simplicity version. So I can always have new simplicity versions. I'm not limited to a certain version. I can always add more jets. But the idea is that the initial catalog is rich enough, so you don't need to do that for a while. So this is kind of the elevator pitch for simplicity. So let's see where we are right now. So okay, this sounds cool, but what has been done, or what do we have actually? So especially with respect to Liquid, because we want to deploy this on Liquid, which is our layer 2. So the language is defined. So this is by Russell O'Connor. He knows what he's doing, and the formal details are basically they're done. The core language is also implemented. So we have C implementation with the Rust implementation. The C implementation is the consensus critical one, and that's done. We are working on the jets, so we have this catalog of jets, and those are mostly done, so you can do all kinds of arithmetic and elliptic curve primitives already. And also we have a lot of jets for elements internal, so you can do anything you can do with elements scripts, like all this introspection, all the governance you can do with elements you can already do with simplicity. Where we're still working is the deployment itself. So where can you use simplicity right now? And we have a simplicity testnet, which is public. You can join it. It's not the Liquid testnet; it's its own thing. And you need a patched elements 4 version. So we have a PR for elements 4. And we're also working on tools. So we have a simplicity wallet, which is what I'm working on. We have a file encoding, and we have a higher level language to write simplicity contracts. And I will talk about all of these things. So the theory is done, and in the practice, there are always, as always, there are a few things that need to be ironed out. So the wallet is a descriptor wallet, so we define simplicity descriptors. What is a descriptor? Maybe who knows what a descriptor is? Who has heard of the word descriptor before? Some people, yeah, descriptors. Unfortunately, descriptors didn't exist at the beginning of Bitcoin, but they are really useful. And Bitcoin Core is currently migrating to descriptor support. I mean, they have a descriptor wallet. The other ones are called legacy wallets. So descriptors help you locate and help you spend your UTXO. So they have information that is not necessarily in the UTXO that help you spend it later. And there's a thing called the taproot descriptor. Taproot consists of an internal key and a tap tree. Internal key and tap tree. The internal key is for the cooperative spend, and the tap tree are the different spending conditions you can use to otherwise spend the UTXO. And the tap tree consists of tap leaves, which have the actual scripts. And right now they include Bitcoin scripts. So this is the way Taproot currently works, but we can extend this to simplicity by saying we introduce a new leaf, which is a simplicity leaf, simplicity tap leaf, which has a simplicity version. So Taproot has versions, leaf versions, we introduce a new version, and then we add a thing called a simplicity policy into that leaf, which now gives this taproot output simplicity support. And whenever we see this, to spend this, we have to satisfy this so-called policy. And I'll talk about what that is. So this is what it looks like. So it's an element descriptor right now. So we have some internal key and we have some simplicity parts. And here you have some policies, or you have some gift. You need to provide a signature to the public keys T and C. And with Elements Miniscript, we recently added simplicity support. So you have tab trees, which can include miniscript and simplicity tabroots. This is policy, simplicity policy. So those policy basically, it defines how you can spend, it defines spending conditions. So what do I need to do to spend the 𝐕𝐵𝑥_0? Basically, this is the recipient. Where does my money go? So you have public keys, you have free, you have hash locks, you have time locks. You can combine these things. You have thresholds. And the interesting thing is what we call the ASM fragment. So you can put a simplicity program into this policy and say, the recipient of these coins is whoever can satisfy my program. And this is interesting because simplicity, like I said, is very general. So you can, this could be, is your knowledge roll-up, or this could be a DAO, this could be something very complicated. So that's the interesting part, the ASM fragment. So the wallet has support for this. It works with elements, with latest elements 4, which with simplicity hatched into it, so we have a separate branch. Right now, we generate an XPub descriptor, so it works on the public key descriptor. You can import more complex ones, and you can also import an ASM descriptor. And then you can generate addresses and send coins around. So this is what we currently have for the wallet. So it lets you interact with simplicity in this descriptor context, which is easier than, or this is currently the only way you can interact with simplicity on elements, right? On the chain. To actually see how elements accepts or rejects your spend, and what simplicity can do for you. So the interesting thing is how to spend an ASM descriptor. So if I want to spend a public key descriptor, I just provide a signature for the public key. Easy, right? We all know this, but the ASM descriptor is interesting because I have a simplicity program, and I need to satisfy this program to spend my coins and to move my coins. And so I can do things like key delegation, where I own a 𝐕𝐵𝑥_0, but I actually give 𝐕𝐵𝑥_0 to someone else without a transaction. So this is kind of inbuilt into this 𝐕𝐵𝑥_0, like a second condition where I say, this other person can also have the 𝐕𝐵𝑥_0, and this is, and I define this as spending time. So I have 𝐕𝐵𝑥_0, and later, much later, I decide to give it to you, or to you, or to you, and to you, whatever I decide to, and I don't need to decide on that when I make the 𝐕𝐵𝑥_0, which is a very powerful thing. You might have heard of graph truth. This is like graph truth. I can do a universal SIG hash. So a SIG hash, well, you know, any protocol is a SIG hash, and that enables L2 channels. And SIG hashes are interesting because they allow you to work with pre-signed transactions in novel ways. And simplicity supports all kinds of SIG hashes, and you can actually put all kinds of SIG hashes into the same 𝐕𝐵𝑥_0 and say, the SIG hash is actually I decide on the SIG hash when I spend the coins. I don't decide on the SIG hash before. And you can do also elliptic cryptography and whatever comes out of that. So that's powerful. And what you do is you write a simplicity program. We put this into an ASM descriptor. You send money, you fund this descriptor, get a 𝐕𝐵𝑥_0, and then you write a satisfaction for this program that you wrote. Right now, you have to write a JSON file, so that's kind of manual right now. the wallet, you give this to the wallet, it constructs a transaction, and then the coins are moved to wherever you wanted to move the coins. We're also working right now on, I'm working on a way to make this a little bit easier, so you can specify what the satisfaction looks like, what the witness data looks like when you make the commitment. But yeah, right now it's a manual spend. So you write a program, any program, say you do the zero knowledge proof rollup, and you want to you find this output, and now you want to do a zero knowledge rollup state transition to where you spend the 𝐷XO to a new 𝐷XO. Then what you have to do is you have to provide a very complicated satisfaction which satisfies this zero knowledge proof verifier, because you have to basically do you have to give it a zero knowledge proof that the state transition is valid. And this can be complicated. This is going to be manual, but you can make it easier with some higher satisfaction logic. I hope I didn't lose all of you guys now, but we will go to something more easier now. So, because we also worked on making it just easier to write simplicity itself, which is to me was a little bit surprising. But it's of course important to write simplicity in some text editor and get useful error messages. So what you can do is you can open a text editor, the text editor of your choice. You can start writing simplicity in this human encoding language, and then you send this to a parser, and it will give you type errors. It will give you, well, there's syntax highlighting in your editor. I think we have some language server bindings or something which you can use in VS Code and other editors. And this will give you a base, if it works, it will give you a base 64 encoded simplicity program which you can use in the wallet and which you can use in all our tools. And the text file is readable and the base 64 is not readable. So one is for humans, one is for the machine, which is why this is called the human readable format. And this is low level, but it's already much more helpful. So this is what it looks like. So this is a key spend, or like a key log. So you have, okay, yeah, it's part of the image is missing, but so this says public key PK, and this is some constant. So this is the public key that is coded in the 𝐷XO. This says message. So this is the 𝐷𝗵 has all. This says 𝐷𝗵, so this is where you write the witness data. This says input, so this is, you just arrange these things into one bit, so you just combine them. And then this says output, and this is the short verifier, so the bit 340 verifier, which takes the public key, the 𝐷𝗵 hash, and the signature, and checks if it all checks out. And then all the program does is it takes these inputs and it will tell you can spend the 𝐷XO if the signature is correct, and it will tell you cannot spend the 𝐷XO otherwise. Obviously, this is a simple example, but this is, I think, more relatable, or this is what we all can understand. And then something that is interesting that 𝐷𝗵 is working on is a domain-specific language, which is high level. So this is more like Rust. It has data types. Simplicity has just the simplicity encoding and the simplicity data, and in this one you have, like in Rust, you have a U30, 34, and so on. You have variables and types. You have control flows, so you have if statements, loops, and functions, which you also don't have in simplicity. And what you do is you write a file in this DSL, in this domain-specific language, and you can compile this into human encoding, which you then can compile into this base 64 simplicity for the wallet and for other tools. And this is higher level simplicity. So the human encoding is low level, and this is higher level. This is still work in progress, but this is what many people are looking forward to, an easier way to use simplicity. this is what it looks like. So there are let statements. It's just one example. So I'm not sure if that's very useful, the program, but it just shows you some of the features. So you have scopes, you have variables, you have some types, and then you have some jets which do certain things. I'm not sure exactly what this program does, but it gives you a feel that you have almost a Rust for a front end for simplicity, which is pretty cool. And this, I think, is more reasonable than JavaScript or anything like that, because simplicity is a language that is highly typed, and I'm not sure if a JavaScript front-end would work, but maybe we have that at some point. All right, what are your next steps? So you've seen simplicity. Now, what will you do after this talk? So you will join the testnet. So you will install elements with simplicity support, and you will install the wallet, and you will join the simplicity testnet, which the steps are provided in the second repo. This is your time to take a screenshot or to take a photograph of this to get the links. Or wait, or like a showgraph. All right, take the pictures, because I'm not sure when these slides are uploaded or if they will be uploaded at all. Oh, cool. So and then you write your first program. So you will install the human encoding parser, which lives in the main in our Rust repo, Rust simplicity. You can look at some example programs. So you have the keylog, and you have other examples. We have documentation on GitHub. We have blog posts on the Blockstream blog, and we have the tech report, which lives in the C repo. And then you can start using the Asm descriptor in the wallet, and you can play around with that. If you want to take a screenshot, Rust simplicity, I think, is the most important of all of them. This is where most of the activity happens, and it's the most user-friendly default. Cool. I'm happy to answer questions, and thank you for staying with me.
Thank you so much. Thank you so much. I would like us not to overlap because Anita Posch has her meeting. So I would like, unfortunately, we don't have time for questions, but big respect for Blockstream and work that is being done. It's truly, truly amazing. Thank you. So we can also give a warm welcome to our next presenter. Ah, no.